Hi there, my name is Maxim, and let's get into the problem. So, the first step here is to draw a diagram. From the diagram, we want to draw the free body diagram. From the free body diagram, we will set up our equations, which will dictate us for the rest of the problem. So, the key thing here is to set up a direction, which will be positive. It can be anyone that you desire, as long as you're consistent. That's all that matters. Here we have tension, frictional force, and the x, normal, and the weight of the block here. For the ball, only in the vertical direction do we have forces, weight, and tension. So from here, Newton's second law, we apply it. So here we have tension minus frictional force is equal to the mass of this block times the acceleration, whereas the weight of the ball minus the tension is equal to the mass of the ball times acceleration. Since they're connected by a pulley rope system, the acceleration that the block and the ball feels experience are the same since they are part of the same system. So this right here would be the system. So here, to solve this equation, you're going to need to do a variable substitution for tension, as shown right here, and then you solve for acceleration and you plug it back in. You should be left with this expression. M2 here is the weight, is the mass of the ball. M1 is the mass of the block. And to solve for the masses, you have the relationship that the mass is the weight divided by gravity. So 9.81. So here, this is plug and chug. You have all those values. The next question was to find the work done by the frictional force. So frictional force here is right here. And we know by definition work is, if you want to do depending on what level you're being taught, you may see a lot of different variations of work. The most common one is with scalar units, and where there's an angle phi, which is the angle between the force and the direction at which the object travels. Here, it was 180 degrees, so it's just going to be a -1 that factors out. So they gave us distance in centimeters, converted it to meters. And we know frictional force is mu times the force of normal times the distance. Plug and chug, I got -0.11446 joules. Now going to the next one, work done by normal force. Now, since the normal force is perpendicular to the direction of travel, so it's going to have 90 degrees, there's no work done. Also, if you see, plug it into the equation, f dot d cosine theta, cosine of 90 is 0. So the math checks out. So for the kinetic, the next, almost out of time. For the kinetic energy at that specific point after travel 10 centimeters, what you need to do is find there's two ways to do this. One way is to, that is started off at rest, so VI is 0. You use find V of F from this expression and then calculate it in for the kinetic energy. A is acceleration, S is the distance, which you already have. And that's just plug and chug.